Hi, my name is Shahnawaz. In this lecture, we will study the limit points and the closure of a set in a topological space. So we'll start with the definition of limit pointers. So we have this definition. So let us suppose that A be any subset of a topological space. See, the topological space is X T. So note that, so we have this space X here, and we have a subset A in this space. So we say a point X in X is said to be a limit point or sometimes we call this an accumulation point. Of A if every open set so a set is open if it is in this fancy T. So if every open set U in T containing X contains a point of A different from X, that is if we take this point X out from this open set, because this open set U this contains X, so this is over U and this is over X, so we remove this point. So if this set, which is U minus X, has a non-empty intersection with A, so if this is true for any open set U in T, then we say this little x is a limit point of A. And now note that we write here X is an element of X, so this X may be inside A or this X may be outside A. So there are pointers in X which are outside A but are limit points of A. So if this is true for any open set, then we say X is a limit point of A. So let us recall this again. So a point X in X is said to be a limit point of this set A if every open set U in T which contain X, and that open set must contain a point of A different from X. That means this U here, this contains X, but this U must contain a point of A different from X. That is why we are subtracting this point from this set U. Now to show a point is not a limit point of A, it suffices to prove there is some open set U in X and U in T which contain no point of A different from X. So it is easy to prove a point is not a limit point, but to check whether a point is limit point, we have to check for every open set U. Let us do some example. So let us consider the topological space So consider the topological space xt where our X has say 5 elements, say A, B, C, D and E, and suppose this over tau is which contain the empty set, the set X, say the singleton A, ACD and BCDE, BCDE. So this is our topological space. So these are our open sets, I mean the empty set, the whole space X, the singleton A, this 3 element set ACD and this 4 element set ABCDE. So these are our open sets. So let A be the set which contain the element say A, B, C. So this is a subset of X. Now let us check what are the limit points of A. So we'll start with A. So this is the check limit points of A, I mean find limit points of A. Find limit points of A. So we'll start with A because A is our first element in the set X. So so this is check for A in X. So this is want to check whether this singleton is this singleton, I mean this point A is in X, I mean this point A is a limit point of A or not. So remember that I just mentioned that to show a point is not a limit point of a given set, it suffices to exhibit a subset, I mean an open set in A for which this intersection sorry, this is non-empty, for which this intersection is empty. So A in X is not a limit point in is not a limit point of A. Sorry, A. The reason being, since this singleton, so this is an element in T, so it is an open set. So this is an open set in X such that if I take this open set and I subtract A from it, so this is an empty set. So intersection, take this intersection with A, so this is empty. So this is not open set. However, if we look at this set ACD, so this ACD, so if our open set is this ACD, then ACD set minus this A, if I take its intersection, so this is actually CD here because we are removing A, and if I take its intersection with A, then this is the set singleton C, and hence it is non-empty. But note that this X is called a limit point if this is true for every open set. So since this is not true for this open set, we conclude A is not a limit point. So let us check whether B is a limit point or not. So this is a check for B in X. So first of all, we'll see the open sets in X which contain B. So this is an open set which contain B, and this is also an open set which contain B. So there are two open sets which contain B. So the open sets in X which contain B are, one is X and other is B, C, D, E. So note that if I take this open set and I remove the point B here and take it as intersection with the set A, then this set is actually A, C, D, E, and this is A, B, C. So the intersection of these two sets is actually BC, sorry, AC. So this is actually A and C. So this is non-empty. So for this open set, this is non-empty. So far we are good. Now let us do the same thing for this open set. Also, if I take this open set B, C, D and E and subtract the singleton B and take its intersection with A, so we'll get the singleton C, and again this is non-empty. So every open set which contain B has a non-empty intersection with A. So this means this B is a limit point. So B is a limit point. Again, if we look at, look at E. So this B is a limit point. Now this C is, I think this is not a limit point, because let us check for C. So check for C. So first of all we have to look for the open sets which contain C. So the open sets which contain C are X and this ACD and BCDE. ACD and BCDE. So if we look at this set, so this is actually A, hence non-empty. So we are good with this set. Now let us take this set ACD, ACD, and remove this point C and look at its intersection, with A. So that is over. So that will again be A, and hence non-empty. Finally, for this set here, the intersection will be, so the intersection will be B, which is again non-empty. So C is also a limit point. Now if we look at D, for this set, D is here and has a non-empty intersection with A after removing D. So we are good with this open set. So for this open set, D is here, and if we remove D, it also has a non-empty intersection with our given set, and for this set we are also good. So D is also a limit point. But E, whether E is a limit point or not, we are not sure. So we are good with this set, and we are good with this set. So D and E are also limit points. So therefore the set of limit points of A are So the set of limit points of A are, so A is not there, so we are B, C, D and E. So these are the limit points of set. So we have this notation. So this is the definition. So let Xt be a topological space and A be a subset of X, then the set of all limit points of A is called the derived set of A. And is denoted by A prime. So we have the other example. So let X D be a discrete metric space, sorry, topological space. And A be a subset of X, then the set of limit points of A is actually empty, i.e. there is no point in X which is limit point of A. Let us see why. So note that a discrete space is a space which contain all subsets of X. I mean all subsets of X are open. So let us check for any point X in X. So let X belongs to X be any point. So we claim that this X is not a limit point of A. Since this X is chosen arbitrarily, so then when we conclude after proving this that A has no limit points. Now to prove this X is not a limit point of A, we should be able to find an open set which contain X and has a non-empty intersection with A after removing this single point. So note that every singleton subset of X is in D, i.e. is an open set, is an open set. In particular, so this singleton X is also an open, i.e. this is in D, is an open set in X. Now to show this X is not a limit point of A, we should be able to find a singleton X, I mean an open set U. So let us write this down here. So to show X in X is not a limit point in A of A, we should be able to find an open set U in X such that U minus this singleton X intersection with A should be empty. So if we are able to find one such open subset, we are done. So since the singleton is open, now let us see what will happen if we replace U with this singleton. So then we have, so this is our open subset X. So from this open subset we have to remove this singleton set here, and we have to take its intersection with A. Now when we subtract these things, we get an empty set. An empty set intersecting with A is actually the empty set. So this means this X is not a limit point. So hence X is not a limit point of A. This means that, so let us first erase this. So since this X was chosen arbitrarily, this means no point of X is a limit point of A. Hence, yeah, or this would imply no point in X is a limit point of A. The reason being, every singleton set is actually an open subset of X, because every singleton is in the discrete metric topology. So that is, the set of limit points of A is empty. Now let us see what will happen if we replace this D with the indiscrete space. Now by indiscrete space we mean the space which has only two elements, i.e. the empty set and the set X itself, which is a trivial topology. So example, let Xi be an indiscrete topological space. And A be a subset of X. Now let us look what the limit points of A will look like. So if A is empty, then A has no limit points, then A prime is obviously empty. So this is A prime here. Because since for any open set U containing X in X is such that U minus the singleton X intersection with empty set is empty. So in this sense, the derived set of empty set is empty. Now suppose A is a singleton. Suppose A is a singleton set. Say A contains a point P. That means P is a point in X. Now what we have to do, we have to look for open sets which contain P. So then the open sets in X which contain P, I mean this indiscrete space has only two elements, the empty set and X itself. So there is only one open set X, I mean that is X, which contain this P. So which contain P is actually is X. So let us write the only open sets in X which contain P is X itself. So let X belongs to X be any point such that this X is not equal to P. So this X is not equal to P. Now let us look whether this X is a limit point of A or not. Now in the open set which contain this X, and let us take its intersection with A. Now this A is a singleton which is P, and P is not equal to X. So this has at least one element in common. So this is P, so which is non-empty, i.e. X is a limit point of A. Here this A is singleton. However, if this X is equal to P, what will happen? So if X is equal to P, then X set minus, now this X is P, and we are taking this intersection with A, which is this singleton P. So this is going to be empty. So i.e. P is not a limit point. So we are first we suppose that this A is empty, then we have this supposition here that is A is singleton. Now suppose A contain more than one elements. Now suppose A has more than one element. Now I claim in this case any point of X is a limit point of A. Let X belongs to X be any point. Then now to check whether this X is a limit point of A or not, we have to first look at the open sets of this space, topological space which contain X. Now in this case we have the only one open set which contain X. Now let us take X and let us remove this point X here and take its intersection with A. Now this A being a set having more than one element, so this intersection is always going to be non-empty. That means this X is always a limit point. So hence X is a limit point of A. So what we proved here, so therefore for any A in X where this X is an indiscrete or topological space, the limit points of A are so this A prime is empty if A is empty. It has any point as it is limit point except, so if A is singleton P, then any point of X is limit point of A except this P. So in this case the limit points of A are any point of X except this P, because when we let here this small x to be equal to P, this intersection is actually empty. So in that case P is not a limit point. And finally, if size of A, so if A has more than one element, then the limit points of A are actually the all elements of A. So in an indiscrete space, for any set A, the derived set of A is empty. If A is empty, it is the whole space X minus this point P. If A is the if A is a singleton set, and it is the whole space X if A has at least 2 points. Now we are going to use this notion, and we are going to characterize the closed sets. So one should note that if we have a topological space Xt, then a subset A of X is said to be open. If A is here, then we call this A. So A is open if A is in T, and we call a subset A to be a closed if its complement is open. So if A is open, then A complement is closed. So we are going to now characterize the closed sets. So we have this result here, this proposition. So it states that, so let A be a subset of a topological space topological space Xt, then A is closed if and only if A prime is contained in A, i.e. if and only if A contain all its limit points. So that is right here, if and only if A contain all its limit points, i.e. when the derived set is contained in A. So let us prove this. First of all, we are going to assume this A is closed. So let A is closed. So first let us suppose this set U is open. This means U complement is closed. Now let us take again the complement. So this U complement is closed and its complement is U, which is open. So complement of a closed set is open. So let A is closed in, so this is a closed in Xt. I mean this A is a subset of X which is closed, whose complement is open. So what we have to prove? We have to prove any limit point of A is actually in A. So suppose P is a limit point of A, that is this P is in the derived set. What we have to prove? We have to prove A contain all its limit points, i.e. we have to prove P is in A. So there are two cases. If P is in A, we are done. There is nothing to prove. Suppose not. Suppose P is not in A. So if P is not in A, that means P is so we have X here, a space, and we have A here, which is a closed set, and we say there's a point P which is not in A. So if this P is not in A, so it is in this set, which is the complement of A. So if P is not in A, then P is in the complement of A. But A being closed, its complement is open. So but A complement being an open set, containing the limit point. Now we are going to use the definition of the limit point. So what we claim? We claim P is a limit point of A. That means if we have an open set U which contain this P, then this intersection is empty. Now since this is true for any open set, this is true for A complement as well, because A complement is open. So this is true for A complement as well, because this has to be true for any open set. So but A complement being an open set and containing the limit point, containing the limit point P of A, we have, so this intersection must be a non-empty set. So A complement set minus this point P intersection with A has to be non-empty. So that is A complement intersection with A is non-empty, because if we add this point to A complement, it won't make any difference. But this is absurd, because we know if we take intersection of a set A with its complement, that is always empty. So this is absurd. This means this P is in A. So hence P is in A. That means, so this P was the limit point of A, i.e. P was A in A complement, and we proved that this P is in A. That means A prime is a subset of A. So because this P was in A prime and we proved this P is in A, this means hence A prime is in A, i.e. A contain all its limit points. Now conversely, we assume that A contain all its limit points. So conversely, assume that A contain all its limit points, i.e. A prime is contained in A. We have to prove A is closed, i.e. we have to prove its complement is open. So we wish to prove A is closed. i.e. A complement is open. So if we prove this complement is open, so its complement will be closure, which is A. Now to prove A complement is open, what we are going to do, let us pick any element Z in A complement. So then Z cannot be a limit point of A, because we know that A prime is in A, i.e. A contain all its limit pointers. So if we take a point Z outside from A, that point is not going to be a limit point of A, because so let Z belongs to A complement, I mean Z is not in A, that is Z is not in A. Then Z cannot be a limit point of A, because A contain all its limit points. So if this is the case, then for this Z we are able to find an open set, say UZ, such that if we subtract from this user this singleton set Z and take its at its intersection with A, it has to be empty. So now since this Z is not in A, this would imply UZ intersection A is actually empty, because this Z is not in A. So therefore now Z not being a limit point of A means there is some open set for which this intersection is empty. So therefore there exists an open set, say U sub Z, such that UZ minus this singleton Z intersection with A is empty, but Z is not in A implies but or this implies UZ intersection this set A is empty, because since Z is not in A. Now if UZ has an empty intersection with A, that means this UZ is in the complement of A. So this implies UZ, so this is over X here, this is over UZ, this is over A, and their intersection is empty. So if we look at the complement of A, which is this set here, this must contain UZ, so UZ is contained in A complement. Now what we proved here, so we chose any element Z in A complement, and we proved for this Z there is an open set UZ, I mean user contains this Z, and this user is contained in A complement. This is true for any Z in A complement. So if this is over X, this is over A here, this is A complement. So if we chose any Z here, we are able to find an open set UZ which contain this Z and is contained in the A complement, which is this set. So that means, so this is true for any Z in A complement. So since this is true for any z in A complement, we get, we have this A complement is actually the union of all these union of all these open sets uz, where uz is contained in A complement. Now each uz being open means this union is open. This means this A complement is open, and hence A is closed. So A complement is the union of open sets. Therefore A complement is open, and hence A is closed. Now we have a definition. So let A be a subset of a topological space, say xt. Then we call the set, then A with combined with A prime. So if we take the union of A and A prime, we call this set the closure of A. Then the set A union A prime is called the closure of A and is denoted by A bar, i.e. A bar is A union, it is derived set. Now we have this result here, proposition. So let A be a subset of a topological space, say xt. Then the closure of A is a closed subset, the closed set. Now to prove this, we will use the previous lemma. Now to prove A closure is closed, it suffices to prove A closure contain all its limit points. So to prove A closure is closed, it suffices to prove A bar contain all its A bar contains all its limit pointers. So that is what we have to prove. Now to prove this, there are two ways to prove this. One is to prove, so this is over X here, this is over A bar here. What we have to prove? We have to prove A bar contain all its limit points, i.e. if X is a limit point of A bar, then this X is inside A bar. So either we have to prove this thing, or if we take a point outside a bar, then we have to prove this point is not a limit point of a bar. So this is the other way to prove it. So equivalently, it is enough to prove that if x is not in A, i.e. if x is in A complement, then x is not a limit point of A. Not A complement, I mean A closure complement. Now let us suppose, so let x is not in A closure, then x is in the complement of this set. So we will prove this x is not a limit point of A. So if x is in the complement of A closure, this means now A closure being equal to A union A prime, this means, so if x is not in A closure, this means x is not in A as well as in A prime. So this implies x is not in A prime, so this x is not a limit point of A. So I think this is enough. So this x was chosen outside the closure, and this would imply this, or we can go further like this. So I think this is enough for this, but if one would like to go further, this would imply that there exists an open set U containing x such that if we look at this intersection U intersection A, so that is actually the singleton set X or empty, because we are not removing X here. So by not removing X here would imply this intersection is either the singleton or empty. So but this X is also not in A, that means this intersection has to be empty. Then U intersection A is empty, so this rules out this condition. So for if X is in U, then as U is open, and this intersection is empty, this would imply X is not in A prime. So thus U intersection with A prime, this is empty. So this U has empty intersection with both A and A prime. Hence U intersection A union A prime, this is empty. Or so let us first erase this. So what we proved or U intersection with A closure, this is empty. So this would imply X is not a limit point of A closure. Hence A closure is closed, i.e. any point which is outside of A closure is not a limit point of A. This would imply all limit points of A closure are inside A closure, i.e. A closure is closed.